What we're going to do is we're going to look at our valence bond theory. Valence bond theory talks about how our covalent bonds are formed. It says that a covalent bond is formed when an orbital from two separate atoms that each has one electron overlaps with each other. So atom A has an orbital with one electron in it, atom B has an orbital with one electron in it. Atom A and B are going to overlap their half-filled orbitals, and when they do, they'll create a new orbital where it contains two electrons, one from atom A, one from atom B, and the two electrons have opposite spins. Now, we can use what we call orbital overlap diagrams to help to identify what's going on and to see how the orbitals that are involved in bonds, or the electrons involved in bonds, are arranged around the nucleus of an atom. When we do these, there are a number of things that we have to do to make sure we do it correctly. The first is we need our Lewis structure of our molecular ion. Then we're going to write our shorthand energy level diagrams for each of the atoms involved. We'll do our hybridization, then we'll show the overlap, and then we can draw our diagrams. So, hybridization. When two atoms are involved in bonds, the orbitals in their valence energy level will blend together. And so I no longer have an s orbital or a p orbital, I have a blend of an s and p. Now I'm saying s and p because, as we've identified, every atom on a periodic table for their valence energy levels has an s orbital and potentially a p orbital. And we know all of the elements in group 1 have an s orbital as their valence energy level. All of the elements in groups 13 through 18 have s and p orbitals, and then the ones that are transitions, or lanthanides and actinides, they all have an s. So when we have hybridization, it mainly involves s and p. And as we'll find out, we can also have hybridization with d orbitals as well, depending on the element. Let's look at the first element that would undergo significant hybridization, or hybridization of interest, and that would be beryllium. Now, as we look at beryllium shorthand energy level diagrams, we see that it has two electrons in the s and none in the p. And there are no unpaired electrons. So this would suggest that beryllium could not form any bonds. However, when we look at compounds out there, we see that beryllium can form two bonds. So the question is, how does it do this? Well, in the second energy level, beryllium not only has access to s, but it also has access to p orbitals. And we can see our three p orbitals here, and they're all empty. So what can happen is that the electrons can become unpaired. And one of the electrons from the s will go to a p orbital, and then the s orbital that still contains an electron and the p orbital that has gained the electron will blend together and hybridize and give us a new orbital. Okay, and so as a result, I'll get two orbitals of equal energy, and they each contain one electron, which now allows beryllium to form two bonds. And because it was made up of blending one s with one p, we call it an sp orbital. We can look further. If we look at boron, we can see boron has three electrons. It has one p orbital with a single electron. Again, we know from experimentation boron can form three bonds. So therefore, we get our electrons in the s becoming unpaired, one of them moving to a p orbital. We're going to blend the one s orbital with two p's to form a new set of orbitals. And so we'll have three orientations of equal energy, and it's called an sp2 because I blended one s with two p's. And now this allows my boron to form three bonds. Again, here carbon, we can see it only has two orbitals with a single electron, suggesting it can only form two bonds, but we know carbon can form four bonds. So the one electron from the s will move to the p, and then we'll blend the s with the p's, and we'll get a new set of orbitals with 4 orientations because I've blended together 4 orbitals, and it's called an sp3 because it was formed by combining one s with 3 p orbitals. And so therefore now my carbon can form 4 bonds. This is a similar hybridization that the other elements past carbon in the same period would form. So oxygen, as long as nitrogen, oxygen, and fluorine, as long as they have only single bonds, would hybridize in an sp3 format. What about if we have expanded octets? So we've looked at the cases where we have our compressed with beryllium and boron, and we've seen now why beryllium forms 2 bonds and boron forms 3. What about phosphorus? Why does it form 5? Well, phosphorus could undergo a sp3 hybridization, in which case that would allow it to form 3 bonds and have a lone pair. But because it has access to d orbitals, it could also hybridize in a second way. And the reason it has access to d orbitals is because its valence energy level is a third energy level, and when n equals 3, I can have s, p, and d. Okay, so we can hybridize those. So the 1 electron in the s will become unpaired. It will move to the d, and then we'll blend them together, and we'll create a new series of orbitals, each that contain 1 electron. And now we can see that it can form 5 equivalent bonds, and it's called an sp3d because I blended 1 s with 3 p's and 1 d. Similarly, sulfur, we know it could undergo a hybridization with its s and 3 p's to form an sp3, and that would allow it to form 2 bonds. But we also know that it can form more than 2, and so it could also hybridize involving the d orbitals because it's in the third energy level. Okay, and so as a result, if we do that, my pair of electrons in the 1s orbital, the pair of electrons that exist in the 1p orbital would become unpaired, and those 2 electrons could each move to a separate d orbital. We then blend them all together, and we get an sp3d2, and so this should be a 2. Okay, and so now we see that there are 6 orbitals of equal energy, all containing 1 electron. And so now this would allow our sulfur atom to form our 6 bonds. So let's take a look at a couple of examples where we can apply this idea. So the first example we'll look at is a fairly simple one, CH4.
So here we are going to look at CH4. So the first thing we have to do is we need a Lewis structure. So and then for just keeping track, I'm just going to number my hydrogens. Okay, now the second thing we need is we need our shorthand energy level diagrams. I'm going to start off with my carbon. Okay, and we can see that our carbon forms 4 single bonds. So this tells us that it's going to hybridize involving the S and all 3 of the P's. So therefore, we know that our carbon, when it hybridizes, it'll hybridize to an sp3. And then we have each of our hydrogens. with their electrons. So our first step was to do Lewis. Second, we show our valence energy level diagrams. Then we show our hybridization. Now we can show our overlap, and we can see that this S is going to overlap with the hybrid. That'll be the bond to the first hydrogen. The S is going to overlap with the hybrid, second hydrogen. S overlap with the hybrid, third hydrogen. And S overlap for the fourth hydrogen. So now that we know what's going to overlap with what, we can do our diagram. And so we'll put our carbon in our center. We'll mark where each of our hydrogen nuclei are. And then we can do our overlapping. So now we know the S overlapping with the P is going to have our sort of fish shape. Our S overlap with hybrid, look like fish shape. S overlap with hybrid, fish shape. And S overlap with hybrid. And that gives us our fish shape. So that's what our valence or orbital overlap diagram would look like for CH4.
Okay, so now let's take a look at a second example, CH3OH.
Okay, for our second example, we're going to look at methanol. So again, first thing we need our Lewis structure. So we know carbon is my central, bonded to 3 hydrogens, which is bonded to an oxygen. Then I have my 2 lone pairs. Okay, so now that I know what my Lewis structure is, now I can start looking at my overlap. And again, I'm just going to label my hydrogens. So I know my carbon, write out its valence energy level diagram. And I'll do the same for oxygen. Now, because it's single bonds for all of them, both of these, when they hybridize, will not need to keep back a p orbital. So they'll both hybridize to an sp3. Carbon will have 1 electron in each of the hybrid orbitals. Oxygen will have 2 of them with 2 electrons and 2 with 1. And then I'll place my hydrogens around. And then I can now show the overlap. So therefore, just going to zoom out so we can see a bit more. So for this hydrogen to carbon bond, which is this right here, it can be an overlap of a hybrid with an S. For this carbon to hydrogen bond, carbon with an S. This would be my 3rd hydrogen on the carbon. I can have a hybrid with a hybrid, for the carbon to the oxygen. Then overlap of a hybrid with an S for the hydrogen on next. So now that I know what orbitals are going to overlap, now I can do my diagram. Put my carbon, my oxygen, hydrogen nuclei. Okay, and again, overlap of a hybrid with an S, fish shape. Hybrid with an S, fish shape. Hybrid with an S. Okay. Hybrid with an S. And then my last one between the carbon and the oxygen will be a hybrid with a hybrid. So it would look like that. Okay, and then I could even go so far as to label all of these as sigma bonds, as they're due to the end-to-end overlap of two orbitals.